Greetings and welcome back. Today we'll start our discussion about relationships between molecules. So we spent a lot of time looking at individual molecules. However, given any two molecules, there exists some type of relationship between them, or no relationship at all, but often there is. So the very first one that we'll talk about is the loosest or kind of most distant relationship, which is called structural isomers. Sometimes this is also referred to as constitutional isomers. But I prefer structural, so that tends to be what I use. However, I want you to be aware that there's two different names for this. I'd like to start this out with an example. This is an alcohol. It's a 4-carbon alcohol. This is a 4-carbon ether. And this is also a 4-carbon alcohol, but you know that this is different from the first one. However, all of these molecules have the same amount of stuff. So they're all C4H10O. And you could go through and count the hydrogens if you want to, or you can take my word for it. But all of these guys share the exact same molecular formula. That is to say, they have the same amount of stuff. However, their bonds are arranged in completely different ways. Therefore, these molecules may have almost nothing in common when it comes to physical properties. They all certainly have different boiling points. They'll have different miscibilities with water, on and on and on. However, they have the same amount of molecule or atoms, so they all have 4 carbons, 10 hydrogens, and 1 oxygen. Therefore, we classify these guys as structural isomers. Structural isomers. And the definition of structural isomers is molecules with the same molecular formula but different bond locations. So I'll give you an example of some things that are not structural isomers. So, for instance, this guy and this guy are not structural isomers because the one on the left is C4H10O. The one on the right has 5 carbons, so it is C5H12O. Furthermore, we could have something like this. This guy has 4 carbons, so this would be C4H8O because it also has a double bond. So it has to be the same amount of exactly every atom within the molecule for it to be a structural isomer. Furthermore, kind of looking at that top right example on the page, the 2-butanol, this molecule and this molecule are not structural isomers because they do have the same molecular formula. However, they have the same bond location, so these are going to be classified as stereoisomers. And we will look at those in the next video. So again, these guys do qualify in that they have the same molecular formula. However, they have the same bond locations. That is to say, basically their names are the same. They're both going to be 2-butanol, but they're only differentiated in terms of cis or trans or R or S, and so we further classify those guys into stereoisomers, which is a much closer relationship. All right, so I'm going to give you an example of this to try, and then we will move into something that is helpful for this. I gave you an example on the previous page for a molecule with 4 carbons and no double bonds versus a molecule with 4 carbons and a double bond, and said that they ended up having different number of hydrogens. So there's actually a way that we can calculate the number of missing hydrogens and use that to our advantage, whether we're going from looking for structural isomers or if we're given a molecular formula and we're trying to figure out exactly how many of those kind of things that remove hydrogens exist. So for instance, if we have C6H10, this is a molecular formula, but just by having these numbers, the 6 carbons and the 10 hydrogens, we can calculate exactly how many of those rings or double bonds exist. And we call those rings and double bonds elements of unsaturation. Right, because this means that the molecule doesn't have the maximum number of hydrogens, so they're not saturated with hydrogens. And one element of unsaturation could be a ring or a double bond. And a triple bond counts as 2 elements of unsaturation. And again, this is useful if we have our molecular formula. We can calculate exactly how many elements of unsaturation there are. And it turns out if something has the same number of carbons and the same number of elements of unsaturation, it will definitely have the same number of hydrogens, so it prevents you from having to add up all of your hydrogens in a molecule. All right, so the way to calculate this is that the elements of unsaturation is equal to the max number of hydrogens minus the actual number of hydrogens. And all of that divided by 2, or multiplied by 1/2. So, for instance, with C6H10, the actual number of hydrogens is 10. But to get the max number of hydrogens, the maximum number of hydrogens in any alkane or oxygen, carbon, and hydrogen containing molecule is going to be 2 times the number of carbons plus 2. And this comes from the fact that all alkanes are just a whole bunch of carbons in a row. And however many carbons we have, I'll just draw 3, essentially we have a repeating unit in here, which is CH2s. The more carbons you're adding, the more CH2s you have. And then you're always just going to have 2 hydrogens at the end, assuming you have a straight chain alkane. And so the way that this works out is this plus 2 comes from the fact that there's just 2 hydrogens at the end. And the 2 times the number of carbons comes from the fact that every time you add another carbon, you add 2 more hydrogens. So the maximum number of hydrogens will be, you take the number of carbons and multiply it by 2 because every carbon brings 2 more hydrogens, and then you add 2 to it just because there's 1 on each end. All right, so the math for this would work out with C6H10 as 1/2 times the max number of hydrogens would be, in this case, 2 times 6 plus 2. 2 times 6 is 12, plus 2 is 14. So the max number of hydrogens would be 14, and the actual number of hydrogens is 10. And so you get 1/2 times 4, and the number of elements of unsaturation in this molecule must be 2. And so essentially what I can do is just draw out 6 carbons, and I need 2 elements of unsaturation. So I could use 2 rings, or a ring and a double bond, or 2 double bonds, and that's what I'll do. Or I could just have used a triple bond just as easily. And now I guarantee you that the number of hydrogens works out to be 10. And we didn't even have to go through the problems of putting hydrogens in. So to double check ourselves, let's draw them in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so as it turns out, any way you draw this, with 6 carbons and 2 elements of unsaturation. So here's 6 carbons, and a ring counts as 1, a double bond counts as another. I can say for sure that since these guys have 6 carbons, and they have the same number of elements of unsaturation, that without going through the trouble of adding up all of the hydrogens, they must all have the same molecular formula. And if they have the same molecular formula, but they're put together differently, they are structural isomers. So all of these guys would be structural isomers. It turns out that if you have oxygens, this same equation goes the same, and oxygens don't matter. If we have halogens and nitrogens, you have to calculate it slightly differently, but we will talk about that in class. All right, so hopefully you can see that this is helpful. This is helpful for two reasons. One is, if you're given a molecular formula and asked to draw a possible molecule, it makes it, I think, easier to do so if you know how to calculate this out. The second thing is, if you have molecules and you're asked for their relationship, you can add up their carbons, their oxygens, their nitrogens, etc., and then just look at the number of elements of unsaturation, which is a substitute thing for adding up their hydrogens. So instead of having to add up their hydrogens, you can just say, well, this guy has 2 elements of unsaturation because it has a triple bond. This one has a ring and a double bond, and that's 2. Therefore, they must assuredly be structural isomers regardless of their number of hydrogens. Hint, their hydrogens are the same. All right. So I do want to tell you one more thing about this, which is that some people call this elements of unsaturation, and some people refer to this as the index of hydrogen deficiency. So essentially, how deficient are these molecules in hydrogens? So calculating the EOU, which is elements of unsaturation, is the same thing as calculating the index of hydrogen deficiency. They mean the exact same thing, and I'm sorry that 2 terms exist, but I want you to be aware of that. All right, thanks. Please practice this, and I'll see you in class.